This is part 2 of section 10.8, power series and interval of convergence. So in this part, what we're going to do is we're going to talk about these important questions. When does a power series converge? And what test do we use for determining the convergence? Now, we've spent a lot of time on our convergence test, but it's nice to know that one of the easier tests is the ones that we use, which is the ratio test. Excuse me. Once in a while the root test, but usually the ratio test. And we're going to talk about something called the interval and the radius of convergence. And so what's going to happen is that these power series may not converge everywhere. They're probably going to converge near that center that we've created our power series at. So we also want to see not just what that interval is, but what happens at the endpoints as well. So that's what the focus of this video is going to be on. So the radius and interval of convergence. So we have our power series, which looks like this infinite series. So we have summation from n equals 0 to infinity of a sub n times x minus c to the n, where the domain of f is a set of all x's where the power series converges. So our concern is to find that domain. And they should all converge at their center, which is C. So C is always in the domain. So we're going to look at three ideas here: whether it converges at a single point, an interval centered at C, or the entire real number line. So here is how we determine the convergence of a power series centered at C. There are three possibilities. It'll converge only at its center, only at C, or there exists a real number R that's positive that the series converges absolutely for the absolute value of x minus c less than R, and diverges when the absolute value of x minus c is greater than R. And our third possibility is that the series converges absolutely for all x. So that R is the radius of the convergence of the power series. So if the series converges only at C, then R is going to be 0, because there is no radius. It's just that point C. If it converges for all real numbers, then R is infinite. It's not really a real number. And then if the set of all values x where the power series converges is an interval, we call that the interval of convergence for the power series. So what we're going to do is we're going to use the ratio test to find the radius and the interval of convergence. And remember that the ratio test tells us that a series converges if our limit of a sub n plus 1 over a sub n is less than 1. So what we're going to do is we're going to find that limit and then determine which values of x where that limit is less than 1. So we want to notice that every time we're asked to find the interval of convergence, you have to check the endpoints, because C is on the interval, but that doesn't necessarily mean that we're at the endpoints as well. What happens at the endpoints? Okay, so let's do some examples of this. So example 4 says, find the radius of convergence and interval of convergence. Be sure to check the endpoints. I'm sorry, I have something stuck in my throat. All right, so letter A, we have the summation from n equals 1 to infinity of x minus 2 to the n over n, which is a power series. So the first thing I'm going to do is I'm going to use the ratio test to determine where it converges and if it does converge. So we are going to have x minus 2 to the n plus 1 over n, and we're going to divide that by x minus 2 to the n, oops, this should be an n plus 1, over n. Simplifying this, we get the limit as n approaches infinity of x minus 2 times n over n plus 1. And now we're going to take the limit of this, and when we do, we are going to get the absolute value of x minus 2. Now remember that absolute value of x minus 2 will be convergent if it is less than 1. So this converges when the absolute value of x minus 2 is less than 1. That's the way our ratio test is set up. So what we have to do is we have to check what's going to happen. So we know that x minus 2 is going to be somewhere in between -1 and 1. So when we simplify this, we get that our interval for x, if we add 2 to both, is going to be 1 is less than x, which is less than 3. So what we've done is we've kind of found our interval here, but we have to check our endpoints to see if we can set x equal to 1 and also x equal to 3 as well. So to find our radius of convergence, let's do that first because that's easier. We don't really have a lot of work to do for this. Remember, that's the total length of the convergence. I'm having trouble spelling there. Okay, it is going to be half the length of the interval because the radius is just half. So we have a length of from 1 to 3 is 2. And we're going to divide that in half. So we get a radius of convergence of 1. Okay, so now let's find the interval of convergence. We have it kind of. We know it's between 1 and 3, but we have to check the endpoints. So first one is going to be at x equals 1. So what's going to happen? So let's set up our infinite series. So we have the summation from n equals 1 to infinity of what happens when we put 1 in our series here. Let me use a highlighter so you can actually see what I'm doing. And what we get is we get -1 to the n over n, which is our alternating harmonic series. Which we do know converges. And you can go ahead and say things like that on the AP test because that's a pretty common series, and that way you don't have to go through the steps of showing the convergence of it. But if it's a series you don't recognize, you need to pick a convergence test and use it to determine whether it does converge or not. And then at x equals 3, we're going to have the following series now. We're going to put 3 in for x, so we get 3 minus 1, which is 1. So we just have 1 over n, which is, of course, our divergent harmonic series. So what we see here is that we can substitute x equals 1 in, because it will converge there, but at 3 it will not. So our interval of convergence, so let me write our entire answer here. So our radius of convergence is 1, and our interval of convergence is going to be positive 1 is less than or equal to x, which is less than 3. So we can't include 3, but we can include 1. All right, part B. Now we have the summation from n equals 0 to infinity of n factorial times x to the n. So we're going to start these the same way every time. Let me just erase this now. I don't really need it. So we're going to use the ratio test to find whether or not we have a radius of convergence other than at the center. This is going to be divided by n factorial over x to the n. And when we simplify that, we are going to get the absolute value of n plus 1 times x. And so as n approaches infinity, so does this. And our only exception is going to be when n equals 0. I'm sorry, not n, x equals 0. Okay, so what we have is that the radius of convergence is only the center point. We have no radius. So that's 0, and it only converges at our center. So we really don't have an interval of convergence. This polynomial is centered at 0, so that's the only point where it converges because our ratio test fails. Right, letter C. Now we have negative 1 to the 2n plus 1 over 2n plus 1 factorial. So again, we're going to start by doing our ratio test. So I'm going to take the limit as n approaches infinity of... Now, instead of writing it as a giant fraction, I'm going to multiply by the reciprocal using the n term. So I'm going to have, for my n plus 1 term, I'm going to have x to the 2 times n plus 1 plus 1. And this is all going to be over 2 times n plus 1 and then plus 1 factorial times, and then I have my original n term, which is x to the 2n plus 1 over 2n plus 1 factorial. Otherwise, that would have been a real ugly fraction. Okay, just cleaning this up a little bit to make it a little easier to see what we have. We're going to have the absolute value of 2n plus 3. So we have x to the 2n plus 3 over 2n plus 3 factorial. And then times x to the, whoops, I'm multiplying by the reciprocal. So then, which is exactly what I didn't write here. So let me flip that one over, I apologize. So this should be 2n plus 1 factorial over x to the 2n plus 1. Okay, so now I have my 2n plus 1 factorial over x to the 2n plus 1. Right, now I can simplify this a little bit. So I get the limit as n approaches infinity of, so when I divide my x terms, I'm going to have x to the 2nd power. Isn't it not a very nice looking x? And when I simplify my factorials, I'm going to have a 2n plus 3 and a 2n plus 2, because then the next term after that would have been 2n plus 1 going down, and they all would have canceled with the 2n plus 1. So when I take the limit as n approaches infinity of this, I get 0, which means that the radius of convergence is all real numbers. And so the interval of convergence is the same thing, all real numbers. So here I just gave you an example of each different type where you have a specific interval and radius. That was example A. And then and you had to check the endpoints to see if you're including them or not. An example where you had no radius of convergence. It only converged at the center point 0. And then finally, the last one, it converges everywhere. So you have a radius and interval of convergence of everything. So we have one more example. And let's see how this one works out. So example D then, we have negative 3 to the n times x to the n over the square root of n plus 1. And our summation is from 0 to infinity. So again, let's do our ratio test. So we're going to take, I should put an equal sign there. We're going to do the limit as n approaches infinity of, we're going to have negative 3 to the n plus 1 times x to the n plus 1 over the square root of n plus 1 plus 1, so that's n plus 2. And then that's all going to be divided by negative 3 to the n times x to the n over the square root of n plus 1. So simplifying this, we get, simplifying our 3's, we end up with a negative 3. We could skip the negative, but I'll just leave it there. Simplifying our x's, we just get an x left. And then we have that square root of n plus 1. And then the denominator is just going to be the square root of n plus 2. And so when we take the limit as n approaches infinity, we're going to get the absolute value of negative 3x. And so then what we have to do is we want to remember that this is going to converge when the absolute value of negative 3x is less than 1. So finding that interval, we're going to have negative 1 is less than negative 3x, which is less than 1. So this gives us negative 1/3 is less than x, which is less than 1/3. Okay, so now we need to check our endpoints. To see if we can include those in our interval of convergence. So at x equals negative 1/3, substituting that in, it's a terrible summation. We have, there we go, from n equals 0 to infinity of negative 3 to the n times negative 1/3 to the n over the square root of n plus 1. So simplifying this, we get the summation. Oh, I'm having trouble making those today. Summation n equals 0 to infinity of those negative 3 and negative 1/3 will cancel out to give us 1. So we have 1 over the square root of n plus 1, which is something that you just can't look at. So what we'll do is we'll compare it to this series. One over the square root of n, which is a divergent p-series. And because of that, it's going to diverge by the limit comparison test. So we know we're not including the negative 1/3. And then if we look at x equals positive 1/3, we're going to have the summation n equals 0 to infinity of negative 3 to the n times 1/3 to the n over the square root of n plus 1. So when we simplify, this does simplify a little different. And what we're going to get now is a -1 left to the n power. So now we have an alternating series that we can check. So when we do that, we can check to see that a sub n plus 1 is less than a sub n. We can also see that a sub n is greater than 0 as x gets bigger. And we can also notice that the limit as n approaches infinity of a sub n is going to equal 0. So this converges by the alternating series test. So you can see why we need all these tests. So what we have then for an answer is this, that our radius of convergence I don't know why I'm having trouble writing the word convergence today, is half of the length of our interval. So -1/3 to 1/3 is 2/3. So that's going to be 1/3. So that's part of our answer. And our interval of convergence is -1/3 is less than x, which is less than or equal to +1/3, because I can include that since the alternating series told me that it converged at that endpoint. Okay, so here is a brief summary of what we just did in this section. So you want to remember that it's a good thing to write, if you can, a transcendental function as a power series of this form, and it's valid between -1 and 1, and that a power series centered at C is called a Taylor series, and that by increasing the degree of the Taylor polynomial, the approximation becomes more accurate. So the more terms we add, so eventually we get a Taylor series. And we want to remember that sometimes the Taylor series only converges at certain values of x, so we need to find the radius and interval of convergence. And there are some functions that are not equal to the sum of their Taylor series, but that's beyond the scope of Calc 2. And if you're going to take more calculus, you'll come across those functions. So this is the end of our lesson on power series. If you have any questions, please let me know, and I'll be glad to help you.